Hey everybody, welcome back. This is Ripley. Today we're going to talk about section 9.5, the dot product. Now, the dot product is a way of combining vectors, but you got to sort of understand what this is really all about. I'm going to show you, I'm going to use an applet from the internet to show you what the dot product is, literally, here in just a sec, and then I'm going to show you the rules and kind of some cool theorems that we get to use. All right, first things first. If I take a vector, all right, and I'm going to call this vector v, and then I take another vector that's not parallel to this vector, all right, so they're in different directions, and I dot this thing. So let's call this thing w. All right, now I'm going to change my colors. If I take the horizontal component of w, remember, w can be written as the sum of a horizontal and a vertical component. All vectors can be written as the sum as a horizontal and vertical component. And remember, w can either be written as, you write it like a, b, or it can also be written as ai plus bj, as can v. V can be written as, well, in this case, it's strictly a horizontal, right? Because it's vertical is nothing, but I could do this as like a1, b1, and then I can write this as a1i plus b1j. Now, what the dot product is you take the product. It's simply a number. It's a scalar. It's not a vector. I take the product of the magnitude of the horizontal component of w. If I'm going to go w dot v, and then I take the magnitude of, let's change colors, then I take the magnitude of v, all right, and I multiply those two values together. Then I get w dot. This is a dot. It's not times, but it's sort of the vector equivalent of timesing. Now this gets really useful. The most common problem that we do is a problem like if we've got a wagon on wheels and we've got a handle right here, right? And we're lifting up at an angle of, I don't know, 35 degrees, right? If I got 35 degrees and I'm exerting a force on this handle, and I want to figure out how much work it takes to drag this wagon a certain distance. Well, what you end up with is you end up with a distance vector, and then you end up with, if you think about it, you end up with a force vector that you're exerting on the handle of the wagon. Now that force vector can be written as the sum of the horizontal component and the vertical component. Now the vertical component does nothing to add to the work done. That's the force that is lifting the wagon up, but it's not dragging the wagon forward at all. So in this case, we would have a force vector, which would just be this, whatever this vector is, let's call this v and let's call this d, right? And it would be v dotted with d. That's how we would write it. Now, you may be saying, wait a sec, but why do we have to worry about the entirety of v? Well, by definition, the way that the dot product works is it's really the projection of the parallel part of v, which in this case happens to be the horizontal part. All right? Now, enough theoretical. Let's actually go to an applet where you can sort of see how this works out. Check this out. This is a pretty cool applet. I'm going to reduce that sucker. All right, check this out. I'm going to keep it simple for you first. Watch this. I'm going to make beta. I want this guy to be b over here. You see this over here? I want this guy's size to be 1. Sometimes this thing's a little bit finicky. Okay, so b is 1, 0. So this is our origin right here. And then here's a. Now watch what goes on here. All right, what I have, see this yellow line? This yellow line is the projection of the horizontal part of red, the horizontal component, and it's written down here. Okay, and then I don't even care about the vertical part. Okay, so these are all written over here. B is written as 1, 0. A is 0.56, 0.91, and these are the amplitudes of both. All right, the dot A dot B is this horizontal part, which notice is 0.56, times B, which is 1. So it should be 0.56. Now, watch what happens. If I stretch this guy out a little bit, let's go 1.51, now notice what happens. Well, B's magnitude is 1.51, right? A cos theta, as you can probably figure out, is that's where we're getting this horizontal component from, is 0.566. If I multiply 1.51 times 0.566, I get 0.855. And as I move this guy around, watch what happens. I get closer. See that horizontal, that yellow part grow? Now notice how green just got really big. That's 0.1. I want that thing to be 0. There we go, like that. Watch the green on the bottom really grow as we get longer. It's because I'm taking B, which is 1.49, and then A cos theta, which is the horizontal projection, is 1.83. And if I go 1.49 times 1.83, I get 2.727, which is pretty cool. Now, you may say, okay, Ripley, what if my vectors aren't horizontal? In other words, what if this B guy isn't horizontal? That's a great question. We'll watch what happens. It's almost as though I just rotate the whole system. Well, what is this yellow part, you may say? It is the parallel component to B. It's the projection of the parallel component of A onto B. Then you take the magnitude of that, which is A cos theta, 1.33 or 1.344, times the magnitude of B. All right, now, believe it or not, watch this. This part's really cool too. Let's keep it simple, put it here. Now, think about this. What happens if my vector goes the other way? What if it goes back here? I don't want you to look. Check it out. Look at that. Now what happens? Well, my dot becomes negative, doesn't it? It has to, because the horizontal component of the red, right, is negative, and the product of negative 0.35 and 1.75 is negative 0.613. Which is pretty darn cool. They rounded, of course. Okay? Okay, now, hopefully that helps you figure some stuff out as far as what we're about to do. The irony is this way of thinking about a dot product, while it's very helpful visually, computationally, it's not as helpful. Because actually, it's really easy to dot two vectors. I got to get rid of avocado green, don't I? That's obnoxious. If I have a vector v, and I'm going to call this AB, which is exactly the same as AI plus BJ, right? They can be written that way. And I have a vector W, and let's call this A1, B1, or A1I plus B1J. Watch how simple it is to dot them. V dot W is simply equal to A times A1 plus B times B1. Notice the I and the J disappear. They disappear. It's a scalar. Remember, this is a magnitude that we're finding. So you simply take the product of the horizontal components of both and you add it to the product of the vertical components of both, and you're done, which is pretty darn powerful. All right? Now, there's some properties. Let's talk about some properties of dot products. Properties. It's not very, to be honest with you, up until a couple years ago, I used to do dot product just over and over with students. I've been doing it for years, but I never really understood exactly what it meant. And I would go ask physics instructors, and I never really got a satisfactory answer, the one that satisfied me. And then I started digging around, and I finally understood. Really, you guys, the dot product is a tool of physicists. We use the dot product most in physicists. And what we're looking for is parallel forces. That's what we care about. All right? Did I write force equals it? This should, by the way, sorry, I just caught that. That should be work. Right? Force times distance. Okay, so let's talk about some products, or some properties. So W dot V is equal to, well, you can probably guess, V dot W because of the commutative property. In other words, if I do V dot W, don't these guys just switch places? And last time I checked, the products, our products are commutative, which is nothing to it. Now, if we have commutativity, what's wrong with me? If I go, don't think of this as the unit vector, just think of it as another vector named U. If I go U times V plus W, you can probably imagine what happens here. We end up with a distributive property. So this is not times, it's dotting. So if I dot U with the sum of two vectors, I can rewrite this as U dot V, because there's no real multiplication of that. Whoa, that was crazy. It's not U dot, or not U times V, it's U dot V plus U dot W. And that opens up a whole world of prospects for us. All right, now what do you think this one is? What do you think that V dot V is? Well, again, let's just let V equal A, B, okay? So do you agree that if I dot V with itself, isn't that just a squared plus b squared, which is really the square root of a squared plus b squared squared, right? And what do we know that the square root of a squared plus b squared is in terms of vectors? Well, it's the magnitude of v squared. Now that's going to be useful for us when we prove something, which is actually it's a really cool theorem. And then last but not least is if I dot 0 with any vector, I always get the 0 vector, which makes sense. Can you see how dot product is really the multiplication analog to vectors, if you would? Now, I'm going to show you a little something. This is pretty cool. All right, I think you'll find it interesting. All right, I'm going to do this. I'm going to let, excuse me, I'm going to let this be v, and I'm going to let this be w. Now, if this is v and this is w, what is this vector's name? Can you tell? Remember, the sum of this vector plus this vector equals this vector, because I go tail to tail and head to head, right? So what's this one got to be? It's got to be w minus v. Okay? Now, I want you to think about something for a sec. Can you see where if I have two vectors, it might be really helpful for me to be able to figure out the angle between them? That might be a really useful thing to have out there, because I could have these two vectors floating around in space, right? And remember, vectors are movable, so I can move them so that they're tail to tail, and then if I can figure out what that angle is between, then life gets good. All right? Now, I'm going to use, believe it or not, I'm going to use the law of cosines to figure out a way to determine the angle between any two vectors. Okay, now hopefully you can see this. Think of these, remember, w is a vector, it's a name, it looks like one of these. V is a vector, looks like one of these. W, or one of these, by the way. W minus v is a vector, it looks like one of these guys. If I'm going to use laws of cosines, then I better not think of them as vectors, but I better think of them as their magnitudes, right? Law of cosines is used with lengths of sides of triangles. And I'm using law of cosines because it helps, I've got one angle here, right, which I'm trying to solve for. So watch how this works. I'm going to take the magnitude of w minus v squared, that's just law of cosines, equals the magnitude of w squared plus the magnitude of v squared minus 2, right, times the magnitude of v times the magnitude of w times cosine of theta. Now this is typically when students go, wait a second, are we dotting or are we multiplying? It's a great question. We're multiplying because these are just magnitudes. They're not vectors, right? We're using lengths of the sides of a triangle. All right, now according to this formula though, right here, we're about to enter into vector land. And watch what happens. According to this, if I take the magnitude of a vector squared, it's the dot product of the vector with itself. So this is w minus v. Ooh, I'm going to need way more room. I'm going to come down here. Pardon my board work here, guys, for a sec. This thing becomes w minus v dotted with w minus v, right? Equals w dotted with itself plus v dotted with itself minus 2 times u dot v cosine of theta. Or excuse me, I just lied. No, I can't do that. I got a little ahead of myself, got a little anxious. Now notice, there's nothing that says that the product of two magnitudes is their dot product. There's nothing that says that. So I'm going to leave this thing as the magnitude of w times the magnitude of v. And then here's my cos theta. Okay? Now watch what happens. This is pretty cool. If we have the distributive property, then we have FOIL. Remember, FOIL is just a generalization of the distributive property. So if I'm going to dot u minus v with itself, what I end up with is, well, can you tell? I end up with w dot w, right? Minus, I'm just doing FOIL here, minus 2 w dot v, right? Plus v dot v, which equals w dot w plus v dot v minus 2 times the magnitude of w times the magnitude of v cos theta. Now you can probably see that a couple things are going to happen. Goodbye to w dot w, goodbye to v dot v, right? And what do I end up with? I end up with negative 2wv. I'm going to run out of room. I hate that. Negative 2w dot v is equal to negative 2 times the magnitude of w times the magnitude of v cos theta, which implies, now I must steal some of this space back. If I divide through, that's cos theta by the way, if I divide through by negative 2 times the magnitude of w times the magnitude of v, I end up with, let's change colors so we see this thing brightly. I end up with the cosine of theta is equal to w dot v divided by the magnitude of w times the magnitude of v. I have an equation. I have a theorem. And that's really helpful. Let's kick over a page, rewrite that thing so we've got it written down. All right, I guess technically, if you really wanted to get crazy with it, if you just wanted theta, I know that cos theta is w dot v divided by the magnitude of w times the magnitude of v, right? If I wanted to solve for theta, I could take the inverse cos of both sides and write that up like that. But this is actually pretty useful right here, and here's why. Let's write a question. What happens? Wow, I just had some heavy carbs at lunch, so I may be slipping into a coma. Bear with me. What happens if v and w are parallel? What's that mean? Well, that means I got a vector that looks like that, call that v. I got a vector, well, that looks like that, call that w, and they're parallel, which implies, doesn't that imply that the angle theta has to be 0? True? You agree with that? However, think about what has to happen. Think about what has to happen if that's going to happen. If these things are going to be parallel, if the angle between them is going to be 0, then what does this imply about w dot v over the magnitude of w times the magnitude of v? What's the cosine of theta? It's 1. If two vectors are parallel, that implies that this guy has to be 1, right? Another question, what happens if v and w are, now here comes a physics word, orthogonal. Orthogonal. Now, what does orthogonal mean? Orthogonal means, I'll write it up here, it means perpendicular. Right? Okay, so let's draw an example. Here's v and here's w. What does that mean about the angle in between them if I move it? Well, it's 90 degrees, right? So doesn't this imply that theta equals 90 degrees? Well, doesn't that imply that the cosine of 90, what's the cosine of 90 again? Oh yeah, it's 0. So really what this means is, this means that w dot v divided by magnitude of w times the magnitude of v is equal to 0, which really implies that the dot product between w and v must equal 0, because the denominator doesn't have the ability to make a fraction go to 0. So I can always check to see if two vectors are orthogonal simply by taking their dot product. If their dot product's 0, you've got orthogonality. Remember, that just means perpendicular. Okay? All right. We're going to play with a whole bunch of problems that deal with dot product. And really, dot product is just kind of an interesting way to think about vector problems. It'll be pretty useful. I think you'll like it. All right? I hope to see you tomorrow. Hope you took some decent notes and wrote down a good problem. And we'll talk to you tomorrow. Bye-bye.
Okay, there's one more thing that I want to talk about, and this is going to be really helpful for you guys in Calculus 3. If you're already in Calculus 3, then you're going to use the heck out of these, okay? It's called scalar and vector projections. I'm going to change up notation just a little bit here, just to be consistent with the Calc 3 textbook. So I'm going to take two vectors. I'm going to call this guy B, and then I'm going to call another guy, let's call him A. And I usually hack these horizontal, worst vector ever. Okay, so what we're going to talk about here, is we're going to talk about, oh, I need to call that A, don't I? Here's A. We're going to talk about what's called a scalar projection. Now, this is just using really simple trig, but think of a scalar projection as if we had two vectors. Now, I've got these vectors sort of conveniently labeled so that I've got B. A appears to be close to horizontal. I've got crappy drawing, I know that, but it is what it is. And I'm going to put a theta in between. Now with a simple right triangle trigonometry, if I look at this guy and I throw a right triangle in there, do I or do I not know that the length of this side right here is going to be, well, what would it be? Well, I know that the cosine of theta, right, times the magnitude of B is going to equal the length of that side, right? Equals question mark, which we're going to call that question mark, right? Hopefully you know that, all right? Now I'm going to use something that we've already used with dot products that we've already learned. I know that cosine of theta is equal to A dotted with B divided by the magnitude of A times the magnitude of B. Now let's look at these things. This notation might be a little bit sketchy for the pre-calculus kids. For pre-calculus, you would have these double vertical lines, which would indicate magnitude of a vector. As you get into Calc 3, they turn into absolute values, basically. Now, remember, this whole thing is nothing but a scalar, right? Because a dot product is a scalar, magnitudes of vectors are also scalars. So I've just got this number. Now, so if I want to know the length of this side of this scalar projection of B onto A, I can actually do it without having to know what theta is. I can actually, by solving for B, absolute B cos theta or magnitude of B cos theta, notice that what I get is A dot B over magnitude of A. It's the same thing. No theta required, which is really nice. Okay, now, it's not just that. What we want to do now is I want to turn this scalar, this side of this right triangle, into a vector that is in exactly the same direction as A. That's what I want. So what I want to turn it from a length into a vector itself. So let's think about how we would do that. I don't necessarily want to have to set up proportions with A to figure that stuff out. And since I know the length of this side before it's a vector, can't I simply multiply it by the unit vector of A in the same direction of A, and I will get this vector, basically. I'll get that for nothing. So if I look at that, think about how I would do that. I would simply take the scalar value, which is A dot B, over magnitude of A, and then I would multiply it by the the unit vector of A in the same direction as A. And we know how to do that. That's just A over magnitude of A. Now we got to be really careful here. I'm going to clean this up. I'm going to turn it into A dot B over magnitude of A squared times A. Now you may be tempted to stick an A squared right there, but hopefully you see that that's not the case, because remember, this guy is a scalar. This guy is also a scalar. And way more importantly, this guy's a vector. So I got my vector right there. All right? So this is the equation right here for that vector projection onto A in the same direction as A from B. It's kind of like what we're doing is we're breaking B down into its component vectors where one of the components has to be A. And I can build orthogonal vectors that way. Now there's a little bit of notation that I want to, excuse me, that I want to address with you guys really quickly. It won't take long, I promise. A dot B, whoops, no, that's right, sorry. A dot B over A, which we know is the scalar projection. The way that we write that is comp little a. So that's a subscript, kind of like a logarithmic base, B. And the way that I think about this is B is projecting onto A. A is sort of passively sitting there, and B is doing all the work, projecting its parallel component onto A. That's the little mnemonic. That's the only way that I can remember. Otherwise, I screw it up. If I take A dot B over magnitude of A squared times the vector A, remember that is a vector. I'm multiplying times a vector. I'm not taking a dot product. This is referred to sort of predictably as, as projection of B onto A. All right? So we've got our notation, we have our two equations, and I think we're all set. I hope this was helpful, and I'll see you tomorrow. Bye-bye.